All right. So last Thursday we write down the three-dimensional Laplacian in two different kind of non-rectangular coordinate systems. One is for cylindrical coordinate system. The other is the spherical coordinate system. So in the rest of this section, we will consider the Dirichlet problem in spherical coordinate systems. As we mentioned before, there are three kinds of boundary value problems, right? One is called the Dirichlet problem, which specify the boundary condition in terms of the solution of the PDE, the U, right, itself on the boundary of a region. So that, and for the Newman problem, we mean that we specify the boundary condition in terms of the first order partial derivatives, okay, especially in the normal direction of the boundary, okay. And the third one is the mixed type, okay, including in some of the boundary we specify the boundary condition in terms of the U function itself. And in other part of the boundary, we specify boundary condition in terms of the directional derivative, okay, in the normal direction. Right. So now we consider the Dirichlet problem, okay, and to simplify, so we consider a simpler case. So we assume circular symmetry, right? Which means that the U tilde are theta and phi is equal to U and phi. So U tilde. Remember, U tilde is the solution of the PDE, okay, in the spherical coordinate. Right. All right. So we assume that U tilde is independent of theta. Okay. All right. So which implies that, okay, the partial derivative with respect to theta, especially the second order partial derivative, okay, with respect to theta is 0. Okay, and so that the Laplacian becomes to here okay, so okay, and plus 1 sine phi of sine phi okay, and which is equal to 0 for our Laplace equation. Any questions? Okay. Remember, theta is the horizontal angle, right? And phi is the vertical angle. Okay, vertical angle there. Okay, so circular symmetry is that the function, our solution, okay, is independent of the horizontal angle. Okay, theta is it. Okay, and now we give explicit. Okay, so we call this is 12.11.1. Okay, and we have expressive boundary condition. Okay, at r equal to r, some big R. Okay, which is described by phi is equal to f phi. Okay, and remember the vertical angle is in between 0 and pi. Okay, so this is 12.11.2. And explicit boundary condition at r equal to 0 for interior problem. Okay, so that we are concerning only the potential, because U is used to describe the potential of some field, for example, electrical field. Okay, and if U specify the potential inside the sphere, okay, then we have a boundary condition at r equal to 0. Okay, and so that it says that the U tilde 0 phi is finite. Okay, for all phi. Okay, so this is 12.11.3. Okay, and explicit boundary condition at r equal to infinity for exterior problem. Exterior problem is that we specify the potential outside of the sphere. Okay, the sphere has radius big R, right? Has radius big R. So we have different kind of problem. One is called interior problem. The other is called exterior problem, right? So that we specify the potential U tilde, right, inside the sphere for the exterior problem, and outside of the sphere. Okay, outside of the sphere up to for R up go to infinity. So we need a explicit boundary at R equal to infinity. And so that in that case, for R goes to infinity, U phi, you usually specify it as 0. So for the exterior problem, when R goes to infinity, then we assume that the potential goes to 0. Okay. So this is 12.4. Okay. So this is our problem there. Okay. Any questions? The interior problem would be inside okay, so that is the interior problem. exterior problem, we will specify the potential okay, so that so for interior problem, the detour R is specified from 0 to big R. For exterior problem, the R parameter is greater than or equal to R, but less than infinity. Okay. So the boundary for interior problem, the boundary would be the sphere. Okay, the surface of the sphere, okay, at with radius big R, and the center, right, of the ball. Okay, and for the exterior problem would be the surface of the sphere, and also go to infinity. All right. Any questions? Okay, if no question, now by the method of separating variable, okay, we let U tilde phi to be GR and H phi. Okay, all right, and we will so now we can go and here as we can see that because this is a factor, right? So we can so this is expression equal to 0, and because of the factor, so that we can consider only the sum of the two terms in the bracket, which is equal to 0. Okay. Because this is equation, this is good for all R in this range or in this range, right? So that means that the bracket is equal to 0. Okay, the bracket is equal to 0. Now, so that okay. So now we look at this term here. So we have d r square and the d gr and the dr. Okay. Right. Times h theta, h phi, I'm sorry. Okay, so that is that term plus and plus gr sine phi d phi sine phi d phi and h phi and d phi. Okay, which is equal to 0. So substituting into 12. Oh, okay, and 1. We have, okay, we have that one. So now we have 1 over GR ddr r square dgr and the dr, okay, equal to minus 1 over h phi sine phi and the d phi dh phi d5, okay, and which will be called lambda, a constant. Okay. So now we render two okay. So we have so we obtain 2 ODEs, okay, and the first one would be d dr r square dgr and the dr, okay, minus lambda g equal to 0, and which is r square and the second derivative, okay, of g with respect to r plus 2r, and okay, I think I write down this one first. So we have 1 sine phi, okay, d phi sine phi dh phi d phi plus lambda h phi equal to 0. Okay, so we call this 12.11.5. Okay, about h. Okay, and for g, so for g we have 1 over by the way, dr r square dgr dr, okay, this one minus lambda gr equal to 0, right? And or explicitly you have r dgr, okay, and the minus lambda g equal to 0. So this is 6. Okay, so we have 2 ODEs here. Now to solve the first ODE, we will take so to solve, okay, 12 in 12.11.5, we let W to be cosine phi. Okay, so we let W as a function phi. Okay, so that w phi is cosine of phi. Okay, so phi is in between 0 and pi. Okay, so you can see w always positive, right? Because cosine function is non-negative. I'm sorry, non-negative. I think. Now, okay, so it's in between 1 and the minus 1. Okay, so which shows that w is in, so that in between 1. Okay, so you can see the parameter w. And all right. Then we have sine square of phi is equal to 1 minus cosine square of phi 1 minus w. Okay, so just write here. Also, okay, the differentiation operator with respect to phi, because in this here we have, and by chain rule, this is equal to phi, right? So, and the derivative of w with respect to phi is minus sine phi. Okay, and dw. Okay, so i.e. we have d phi is equal to dw. Okay, so you can see that here, this one. Okay. Okay. So we have this nice property. Okay. And define h tilde w to be h phi w. Okay, so and phi w is you can set up cosine w. Okay, for okay. So here the cosine has range from 0 to pi. Okay. Okay. And okay. So now we define this function, and then h phi is equal to h tilde and the w phi, which is h tilde of cosine phi. Okay. So once we find h tilde, then we can find the h phi, right? And okay, so now, now we look at the sine phi and d and h phi d phi. Okay. All right. So let's see. All right. Maybe so now dh phi d phi, okay, becomes to minus sine phi and the dw. But so this is this differential operator is equal to this one, and h phi now xh tilde, and so w okay. So this is implies that sine phi one over sine phi and d5 and sine 5 d h phi 5, which is equal to dw, okay, because this differential is equal to, so this is equal to minus here, and and we have minus sine square 5, okay, and the d h tilde w, okay. Is that okay? Because that this one is equal to minus d here. This is equal to minus d dw, right? And inside the bracket, this is sine 5. We can see sine 5 times minus sine phi, because here, right, dw. Okay. All right, so this is equal to dw, and the sine square 5 And finally, the square of sine 5 is equal to 1 minus top square, which 1 minus top square. Okay. Okay. So things maybe I'll say. Okay. Now the ODE in 12.11.5 becomes to dw 1 minus d square dh tilde w dw plus lambda h tilde w. Okay, yeah, lambda h tilde w equal to 0, and so this is equal to d square h tilde w dw minus 2w dh tilde dw plus lambda h. Okay, and when you look at this one or that one, okay, you can see that it's a famous ODE. Okay, the famous ODE we encountered in chapter 11, right? The 5th section when we talk about the Sturm River problem. And so this is the Legendre equation, right? Okay, so this is the Legendre equations with parameter lambda there. Any questions up here? This is Legendre equation. And we know a general solution of Legendre equation. Okay, so a general solution, all right, of the Legendre is here. It's h tilde w is c1 y1 w plus c2 y2 w. Okay, where y1 w can be expressed here by a to k and w to k's power, and y2 w is another series sum a to k plus 1 w to k plus 1. Okay, with a0 equal to a1 equal to 1, and a m plus 2 is equal to m times m plus 1 minus lambda divided by m plus 1 m plus 2 times am for all m greater than or equal to 0. Okay? Okay, so the coefficient of these two series sum, okay, has been specified here. So you can see that if lambda is not equal to sum m times m plus 1, then this is the infinite series, okay, as we know. But if lambda is equal to sum m times m plus 1, right, then one of the series is a polynomial, okay? It's a polynomial there. Okay, and so, okay, for physically meaningful solutions, we must have lambda is equal to m times m plus 1. Okay. For n equal to 0, 1, 2, etc. Okay. Okay. All right. And H delta W is equal to P N W. The Legendre polynomial of degree n. Okay. Okay. And this one are solutions of the gender equation. Okay? Right. Any questions? All right, so we find maybe. Okay, so that so we have this one. So maybe I define, okay. No, just equal. Okay, and with lambda equal to n plus 1. Okay. Now the ODE in 12.11.6. Okay. Is the Euler-Cauchy equation Okay, so I believe you have solved this kind of equation last semester when you study ordinary differential equation. Okay, so this differential equation is called Euler-Cauchy equation. Okay, and the solution. So so oops. Okay, so I have to stop in 5 minutes. So that it can be character the characteristic equation. Okay. The Euler-Cauchy equation xa a minus 1 plus 2a minus n plus 1 equals 0. So this implies that a is equal to n or minus n plus 1. Okay. So that G, so we define R equal to Rn and G n star R equal to R n plus 1. So this is corresponding to A equal to n, and this corresponding to A equal to minus n plus 1. Okay, because they specify the exponent. Okay, the exponent. Okay, so these are solutions. Okay, so these are solutions of the Euler-Cauchy equation. Okay, and so that as we can see that so that UN R phi defined to be an Rn and the Pn cosine phi, and we define Un star R phi to be Bn divided by R to the n plus 1's power Pn cosine phi for n 0, 1, 2, etc. Okay. Okay. For the interior problem, so this one so now so for the interior problem. Okay, so this solution will be used for interior problem. Okay, because that so this is a solution good for, so this is good for interior problem. Okay, and this is good for exterior problem. Okay, because when for exterior problem, when R goes to infinity, this is go to 0, right? It's good. And but if but it is not, because when r equal to go to 0, when r goes to infinity, this is go to 0. But when r go to 0, this is unbounded. Okay, so this cannot fulfill with the boundary condition at r equal to 0, because we want that the u function should be equal to, oh, by the way, I forgot. Sorry, got to put tilt. Okay, so for each exterior problem, okay, the potential within the sphere with radius r x r phi equal to summation n from 0 to infinity un r phi. So this is n equal to 0, an, rn, and the pn cosine phi. Okay. Oh, all right. And pi. And for the exterior problem, the potential outside I forgot to. Okay, I think I have to stop. But let me write down the boundary condition. The boundary condition at r equal to r, which is equal to an, rn, pn cosine phi is equal to f phi for. Okay. All right, so I think I have stopped here, and I'll continue the discussion on Thursday. Okay. Sorry.